Okay, it's 8 a.m. Sharp in California, and good morning to our participants from the North America, and good afternoon to tinyML experts and enthusiasts in Europe and Middle East, and good evening to tinyML experts in the Far East. My name is Evgeni Gousev. I'm from Qualcomm AI, and I will be the host of the webinar today. So before we start, I would like to acknowledge that tinyML has been growing quite a bit. We started this webcast series about 3 months ago, and the community has doubled since then. So we are about 3,000, or actually 3,000 people now, and it keeps growing every day. One thing you may have noticed, in addition to this bi-weekly tinyML Talk webcast series, we also started tinyML from the local groups. We had one from Montreal last week. There will be one coming from Phoenix next week, one from the Benelux, from Europe, and then from the Southern California. So you're going to see more and more activities happening in the tinyML, both in terms of the bi-weekly presentations and also more and more local events, and hopefully we'll have more real meetups, in-person meetups starting soon. So before we move on to the technical part, I would like to acknowledge our sponsors. The list of our sponsors also keeps growing, kind of a reflection of the community growth, and it's also a reflection of the value that tinyML offers to this community. So specifically, I would like to acknowledge H-Impulse, Maxim Integrated, Sense, and our new sponsor, Reality AI. Reality AI, it's a company that offers optimized feature discovery and very small embedded code with no open source, and it focuses on things like bill of materials optimizations, and tools also for managing data collection. It's a very, very interesting set of tools specifically for this market. And if you're interested in being one of the sponsors, there are more slots available. Please contact Betty at tinyml.org. And in addition to the annual sponsors, we have sponsors that can support specific events. So today it is my pleasure to also acknowledge H-Cortex to be our sponsors for special sponsor for today. H-Cortex, it's an international company. It's a startup. They're based in Tokyo and in Singapore, and they also offer automated tools to do co-design of hardware, software co-design for very energy efficient machine learning for IoT and edge type of applications. Thank you for your sponsorship. We are going to continue with our usual kind of bi-weekly cadence. So the next presentation will be in 2 weeks as usual, 8 a.m. Pacific time. One will be coming from the San Diego area. It's Venkat Radgat from Tiny Vision. He is going to continue talking about the low power CV, and the second one will be coming from the academia, from Professor Teocharis from the University of Cyprus, and it's also going to be a topic on the computer vision at low power. And our calendar is quite busy for the talks, and if you're interested in being one of the future speakers, please contact talks@tinyml.org. And at this point, it is my great pleasure to introduce our first speaker, Tomer Malach from DSP Group, and he will be talking about AI, ML, SoC for low power mobile and IoT devices. As I said, Tomer is from the DSP group, and he's responsible for AI hardware there. And at the same time, he is pursuing his degree at Ben Gurion University in Israel, where he also received his degree with honor in electrical engineering. And his research focus is on compression and hardware for machine learning models for edge devices. Okay, Tomer, the stage is yours. And if you have any questions before you go there, there is a Q&A bar in Zoom. So please use the Q&A bar to post your questions, and then we'll answer them during the presentation. So please try not to use chat. The Q&A bar is a better place to ask your questions. And we'll ask questions during the presentation and at the end as usual. Okay, Tomer, go ahead.
Okay, thank you, Evgeni, and thanks for tinyML Foundation for having me here. I'm really excited. And today I'm going to talk and present the work that has been done using all the teams in DSP group for developing AI/machine learning SoC for ultra-low power for mobile and IoT devices. It's not my private work. A lot of people are invested much of time by developing this unique SoC. So the agenda for today's talk is the following. I will start with a background on and motivation why using DNN deep neural networks on edge devices, and then we will continue to talk about the cost and the challenges that deep neural networks face us when we want to deploy them on remote devices. Then the art of the talk will be how we can accelerate deep neural networks on SoC. And we will talk about two aspects. The first one is the computation optimization, and the second one is the memory optimization. Then I will conclude and show some results and present the summary of the talk. So let's start with a background. Deep neural networks, as I'm guessing most of you are aware, are in the core of AI research for many, many years. They have many applications and used in a wide range of areas. They're used for analyzing audio, in proximity, gestures, imaging, and many, many more fields. And the motivation and interest to use them can be demonstrated using the ILS VRC winners over the past decades. In the following table, you can see the top 5 error rate of all the winners across in the past decades. And you can see the exponential improvement in the top 5 error rate across in those years. Also in the graph, you can see the human performances, the top 5 error rate of human being in the image recognition task that evaluated by Roskovsky and its colleagues. And just a second, and in this graph, from 2010 up to 2015, we can notice AlexNet that was the first CNN-based winner in this computation that was composed of eight layers. Then we can see in 2014, the VGG networks and GoogleNet that was contained around 20 layers. And in 2015, we can see ResNet. And here we have two interesting points. The first one is the major increasing in the depth of the networks. And also, it is the first time that the ILS VRC winner outperformed human being in image recognition. From them, we have the squeeze and extraction net, and the continuous, it just continued to evolve. So with so many applications, what is the problem with deep neural networks? When we are taking some network and try to improve it, usually the model becomes more and more complex, and the complexity is expressed by two main things. The first one is the required memory capacity, how much memory we need for storing the model. The second one is the number of computations, how many computations we need to execute in order to run the models. And in the following graph, you can see those both aspects. The x-axis represents the number of giga operations you need to perform for executing each one of these models. And the size of the circle represents the number of parameters that compose the model. For example, Inception V4 contains around 30 mega parameters, and you need to execute around 20 giga operation for implementation. Its top one accuracy that expressed by the y-axis is around 80%. So both of these requirements are conflicted directly with tinyML low power requirement. And now is the question what we can do. But in general, the AI development process, it starts by using one of the frameworks. We have various frameworks such as PyTorch, Keras, Chainer, and many, many more. Then we usually store the model in one of the standard formats, such as TensorFlow Lite, ONNX, etc. And we wish to run the model in a dedicated SoC for implementation. And you can see the size of the SoC comparing to human finger. But now, during this process, we can add the optimization. So the optimization process it's quite similar. We are starting from the framework and wish to run the model on the SoC. And during the last years, there are many, many words that present different types of software optimization. We have shrinking or pruning. Pruning is a process that set low magnitude weights to be 0, or shrinking that remove certain parts of the network and by that shrinks the model. We have quantization that can apply both the data and the weights and represent the data and the weights with less bits than the original representation. Knowledge distillation, etc. We have multiple software optimization types. But now is the question, how can we use the hardware for optimize those models? For one aspect, to support all the software optimizations, and also to take a fixed model and run it at the efficient possible way on the dedicated SoC. So the art of this talk is how can we accelerate DNNs on an SoC? And we'll talk about two aspects. The first one is the computation optimization. And in this aspect, we'll talk about an efficient control unit and how we are achieving the highest time utilization. The second aspect is the memory optimization. How can we optimize the memory usage? And we will talk about dequantization of weights and entropy compression that apply on weights, and also pooling on the fly, which is a unique process that integrated in our SoC. So let's start the talk of dedicated hour optimization by talking about the following, the efficient control unit. So the basic operation in each deep neural network is MAC, multiply and accumulate. We are taking the input data and multiply it by the correlated weight. Then we sum all the result, add some bias value, and output the result to the next layer, or the output of the network. But which weight and which data should MAC? Who controls the flow? In software, it's really easy. The programmer writes some code that controls the flow. But in hardware, we are using something else. We are using an hardware generation hardware unit. We are calling it an AGU that controls the entire flow. The purpose of the AGU is to generate three addresses: the read address for the weight, a read data address for the input data, and write address for the result of the neuron. The second thing we are using, we are achieving the highest time utilization. Pipeline architecture is critical for efficient implementation and acceleration of deep neural networks. Instead of using non-pipeline architecture, we are using a pipeline architecture. We are limited by the number of clock cycles of our clock. So at each clock cycle, we have a MAC operation that executed, and by that we are achieving the highest time utilization. All the cycles execute one MAC operation. And to ensure MAC operation within each clock cycle and avoid starvation, storing is not an option in our system. So now we'll talk about memory optimization, but if there are some questions from the audience, I will be glad to hear them.
Yes, again, there is a Q&A bar on Zoom, so if you have questions to Tomer, please submit it there and we'll answer it. Okay, Tomer,
okay.
Please go ahead.
Let's continue. So the memory optimization. Here, let's start talking about the dequantization. Quantization of weights and also for data has been proved highly effective in the recent years in many works and academic papers. Instead of using the 32 floating point bits that usually the developing frameworks use, we can represent those weights with much less bits. So to best exploit the actual weights range and not using a general 32 floating point bit representation, we are using asymmetric quantization that generates low bit weights. In addition, it's important to mention that quantization per channel is very efficient and have been proven to be significantly increase the efficiency comparing to quantization per channel, meaning that in convolutional layers and depth-wise separable convolutions, the usage of quantization per channel instead of quantization per channel will be much more efficient. So inside the SoC, we have a dequantizer hardware unit that expands low bit weight into fixed length bit weights before the MAC operation, meaning that the memory stores the weights with low bit representation. The dequantizer expands those weights into a fixed length weights, and then the MAC operation executed.
So Tomer, there is a question from the audience. Can you quantify what is the advantage and disadvantage of asymmetric quantization? Could you elaborate on this?
Yes, sure. Asymmetric quantization comparing to symmetric quantization can be demonstrated in the following slide. Here we are taking the full range of the weights, the actual weights range, meaning we are taking from the minimal weights to the maximal weights and define this as our range, weight range. Instead, in contrast to that, in symmetric quantization, we are taking the maximum absolute value of the weights range. In that way, we can see that asymmetric quantization exploits better the actual weight range in comparing to symmetric quantization.
Okay, thank you.
There are more questions?
Actually, there is one more question from Sanjaya. What are the parameters you use while performing quantization? Are there any parameters?
Actually, this aspect is mostly depend on the AI developer, and trial and error will be the best way to know what is the number of bits that can represent the weights range. We are supporting all the number of bits from 1 bit per weight into 16 bit per weight, but the fixed size of the bits per weight can be determined by the AI developer.
Okay, thank you.
Okay. Entropy compression. So for those who are not familiar with weight pruning and what it is, weight pruning process is a process that takes deep neural networks that contain dense weight matrices and make them more sparse, meaning that instead of using dense weight matrices, we are using sparse weight matrices that most of their values are zeros. When we are using sparse weight matrices during the DNN inference, an entropy compression algorithm can be very effective and can compress easily the data, the weights here. So first, we're applying a pruning process, quantize the weights, and then we're applying the entropy compression. Entropy-based variable length coding is a type of compression that assigns different code lengths for each code word based on its probability, meaning that instead of using fixed lengths, fixed length weights, we are using different lengths to represent different weights according to the probability of the weights. And let's see an example. So for the simplicity of the example, I took a case that we have only 4 weights, and by that, those weights are encoded using 2 bits. We can think about the encoding process as structuring a binary tree in depth of 2. All the weights are placed in the same depth, and the encoding for each weight can be generated using transaving in the tree. By that, the encoding of W0 is O. And as you can see, again, all the weights are placed on the same depth. The entropy compression reshuffles this structure. Now, common weights, such as W0, are going higher in the hierarchy, and non-common weights are going deeper. This affects the new code lengths of each weight. Common weights are now getting short code, comparing to non-common weights that now are getting much longer codes. And this helps us to lossless compress the weights inside the neural network. To decode those weights, we have a hardware decoder inside the SoC that at each clock cycle extract one valid weight, and this again for avoid any starvation in the system. Yeah. So how the entropy decoder works? Actually, it's very simple. Instead of using an external memory that sends weights to the Mac, now we added a weights decoder in between them. The memory now says a compressed version of the weights into the weights decoder. We are using a code extractor unit that splits the weights from each other, since now each weight have its own independent code lengths. Different weights can have different code lengths. If the weight is common, using an internal lookup table, the compressed weight is decoded. Alternatively, if the weight isn't common and we want to store it inside the lookup table, the uncompressed weight is placed inside the compressed bit stream, and the code extractor can send the extracted bit stream into the MUX. The MUX select one of the output from the lookup table in case the weight is common, or from the code extractor if the weight isn't common. Then the MUX write it into a buffer, and the Mac takes the weights from the buffer and not from the external memory. So we examined this compression algorithm on AlexNet with 16-bit weights, and you can see here the result. We trained the AlexNet on CFAN10 benchmark. We trained 4 different models and with different sparsity levels, as you can see in the table, and obtained the sparsity using the TensorFlow optimization tool. As you can see, the top 1 accuracy of each model is quite the same. And then we took the weights of each one of the models and compressed them using 7-zip package. 7-zip package is a compression package of lossless compression algorithms. And we wrote here the best result of the best lossless compression algorithm. Then we took again the weights and applied our compression algorithm to the weights file. And as you can see, we got almost the same result comparing to the best 7-zip algorithm. And at some cases, we even outperformed the 7-zip best algorithm. But the important thing here, it's not only the compression ratio, but rather that our decompression method, it's much faster. At each clock cycle, one valid weight can be extracted, comparing to the 7-zip algorithms that are much more complex.
So, Tomer, there is a question from Mike on entropy compression. So the question is the entropy compression Hoffman-like, which is unbalanced, and the tree use proportion of common weights to balance the tree? How does that happen dynamically? Is there pre-parsing of the weight populations when you do the entropy compression?
Okay, so since we are training the deep neural network offline, we are knowing the weights. And when after we train the model and we are getting the weights, we can compress them offline and select which one of the weights will be stored inside the lookup table and which one won't be stored inside the lookup table. Regarding all the details that involve the actual decoder, we are about to publish a paper that describes in details all the structure of this decoder. And for those that interest are more than welcome to contact me.
So Tomer, it may be a good idea to publish this paper, to mention this paper either on the tinyML LinkedIn page or on the forum, so people can kind of get access after the presentation when it's available.
Okay, but to answer in more detail about the question, this question, the structure of the weight decoders allows us to decode each one of the compressed weights in one clock cycle, and the code extractor is the unit that splits the weights between each other and detects the length of the compressed code.
Okay.
So again, this decompression method, it's much more faster than 7-zip best algorithm. We repeated the experiment also with VGG 19 and got the same result. Again, minor gap between our algorithm to 7-zip algorithm, but with much faster decoding time. Pooling on the fly. Pooling is a common operation in deep neural networks and used for downsampling. Instead of using large matrices, we can pool them and use small matrices in the next layer. But in many cases, the pooling operation can be executed on the fly before the activation function is applied. For example, ReLU that followed by a max pooling operation can usually be swapped and combined into a single process. To demonstrate this, let's look on the following scenario. A common case that we have a convolution layer with ReLU activation. After we are executing the convolution and apply the ReLU for all the results, we need to store the results inside the memory. Then we retrieve all the data back to the max pooling to perform the max pooling, and we need to store it again inside the memory. Alternatively, what we can do is the following. We can take the convolution and execute it, then apply immediately the max pooling, and only to the pooled result, apply the activation function. By that, we are reducing two things. First of all, we are calculating the activation function only to the pooled result, meaning to the smaller matrices. Second is the number of memory accesses. Instead of storing all the convolution results in the memory, we are storing only the pooled layer after the activation inside the memory. So let's see the results of this SoC on several test cases.
Before we move to the results, Tomer, there are two questions related to the algorithms. So
Yes.
One is a popular question from Sanjaya. When you perform such quantization, is there any loss in performance, let's say accuracy, and by how much?
Yes, and it's hard to answer this question because it's very dependent on the model. Some models can be quantized into 2 bits per byte and you won't see any effect. and some models that below 8 bits per weight will be dramatically decreased. So it's very dependent on the model. Usually trial and error, it's very common method to know how many bits you need for representing the weights. But there are several researchers that invest this problem and suggest different ways how to select the number of bits per weight.
And also there is a question from Andre on algorithms. At what sparsity level do you begin to get advantage over a dense matrix? Is there like a number?
No, actually from the 1% we are getting advantage. The sparsity decreasing the entropy of the weights. And in the minute we are starting to decrease the entropy of the weights, we are increasing the possible compression ratio. So 20% of sparsity will generate some compression results, but also 5% of sparsity also will able us to compress the data in deep neural networks.
Okay, let's move on to the results. Thank you.
Okay, so let's see several test cases of that we are used this SoC to run several deep neural networks. You can see here 3 test cases of low edge keyword spotting with deep neural networks fully connected, and also with convolutional neural networks and depth-wise separable CNN. And you can see the power consumption per inference for all those networks. Also, we have a fashion MNIST CNN and CFAR10 CNN. The source of all those models can be reached using the following links, and the power consumption per inference allows us to run all those models on edge devices in very efficient manner. Okay. So let's conclude this, the talk. We talked about that deep neural networks are a powerful tool for solving multiple AI tasks, but the problem with them is the number of computation and the required memory size. And we saw how can we accelerate deep neural networks on an SoC and do optimization for the algorithms for maximizing the available output that we have. We saw the results, and now I will be happy to answer any of your questions.
Yes, Tomer, thank you. Very interesting presentation. We have time maybe for a couple of questions. There are 2 questions related to the hardware. One question from Aya. The question is, how do you do pipeline in the hardware?
Okay, so as I mentioned, there is a MAC operation. We are aimed to do a MAC operation in each clock cycle. So we separated all the graph that structured the deep neural network into several levels, and by that we are able to design a pipeline architecture that each clock cycle execute and analyze a certain part of the network, and it's not able to stall the rest of the system.
Yeah. And there is one more question on the hardware from Phil. Designing an SoC is very complicated. Do you have a working implementation, and can you share it?
This SoC is actually a work we invested in the past 2 years. It's very difficult to build such an efficient SoC, and actually it's available now.
Yeah, so if people would like to get it and kind of use it to play with this, what would be the way? How would they?
They can contact directly DSP group, and we will be happy to take it to the next level.
Okay, great. Thank you, Tomer. And I think well, there are more questions. We'll probably answer them on the forums. And there is one question that I'm going to answer. It says, could you share the slides? I think it is fantastic. I definitely agree. It is fantastic. Thank you, Tomer. And the slides will be available on the tinyml.org website, on the forums, and also the videos will be available on the tinyML YouTube channel. It's YouTube tinyML by tomorrow. So I think all this information will be posted and the slides will be available because this is the tinyML spirit, community spirit to have this information available to the whole ecosystem. Again, thank you, Tomer. Our special sponsor today is Edge Cortex. It's an international startup based in Tokyo and Singapore, and they focus on optimizing machine learning for doing co-design, hardware, software, core search engine, and it's quite unique technology for edge type of applications, and they do it at very low latency and extremely energy efficient, kind of in a tinyML fashion. Our annual sponsors are Edge Impulse, Maxim Integrated, SenseSense, and Reality AI is the new sponsor who joined last week. And for more sponsorship, please contact Betty at tinyml.org. So tinyML, the mission of Edge Impulse is really to make tinyML deployment as easy as possible. So they develop a lot of tools and techniques, and they keep adding more libraries and more features to help developers to deploy tinyML on their devices. So check out their website if you're interested in more information, and if you would like to get a free account to get started with this technology. So Maxim Integrated is a big established company. They have a lot of activities. It's a silicon and hardware company. So they do work in many different areas, but specifically to tinyML, it's sensors, low power processors, and they have AI acceleration coming soon. Also check out their website and announcements there. SenseSense, it's a startup based out of Switzerland, and it's formerly known as AI CTX, and they build ultra-low power devices based on neuromorphic architecture, and it can be used for many different applications, embedded, mobile, edge devices, and so on. It's kind of inspired by nature. Reality AI, as I said, it's a new sponsor, and they go beyond the developing workflows. They do a lot of optimization, and it's a next generation AI tools for productization of tinyML. They do feature detection and extremely small codes. You have a lot of sensors there, and it does a lot of automated data and collection and so on. And the key there, it's not open source type of issues there. As usual, we are going to have our next talks in 2 weeks at the same time. So we hope you're there. And at this point, thank you for your attention today. Thank you for your active participation, for questions. Thank you, our speakers, for the great presentations. I think both of them were amazing. And thank you for our sponsors. I think your support is quite important to keep this webcast going. So thank you again, and we'll see you in 2 weeks. And the local events will be happening in between. I think the tinyML Phoenix is going to be on the 28th next week, and then we'll have more local events happening in August as well, in Benelux, Southern California, Irvine area, and so on. Thank you.